Hi guys, welcome back. So decided to make a video for you today about estimators. Okay, this is just kind of the next step in our progression. We're just slowly adding new things to our statistics, different way of talking about things, different way of describing things. A couple of things that we've talked about so far. Last time we were talking about the mean of a sample and the sample proportion, right? And remember we were talking about the idea that the expected value of our sample mean should be the mean of the population. And we were also talking about the idea the expected value of our sample proportion, the proportion that we get from our sample, should be more or less equal to the population proportion, right? Because it's a proportion of a certain number of successes to a total number. Okay, so these are some ideas that we've been talking about. Okay, now some of the other things that we've kind of been looking at is the idea that when we did normal distributions before, right? We said, well, this specific item has a normal distribution, whether it be heights or distances or sizes, whatever it was. We said this has a normal distribution, and we said here's our mean and our standard deviation, right? And we started talking about these ideas. And then when we did that, we said, okay, well, what is the probability that a single random event, right, that a single random person or single random tree has this specific height or size or number of rings or whatever, right? So we were always talking about what's the probability of a single event occurring, right? We extended a little bit when we were talking about like binomial distributions, but still, even with binomial distributions, we had a set number of times it was occurring, like 20 coin tosses, and what is the probability that we're going to get exactly 7 heads, right? And so it was still, if I do this 20 times, what's the probability that I'm going to get 7 heads? It wasn't flexible on the number of times that we were repeating it. It wasn't looking at, well, what if I do this, if I flip a coin 20 times, but then I repeat that 5 times, now what are the statistics going to look like? We didn't do any of that before. That's kind of what we're getting into now. And so this is going to get us into, today's going to be a little bit deeper, and then starting the next time, we'll really start to look at a little bit more of those comparison statistics and looking at larger groups and things like that. All right. So today we're looking at something called an estimator. All right. So when we have a specific statistic that we're looking at, whether it be a mean or a variance or whatever else, we're going to define that temporarily as being theta. Okay, so that is the parameter. That's the parameter that we are trying to describe. All right. Now, when we describe that parameter, a capital T represents an estimator. Okay. And that estimator is a function of values in the sample, so taking certain data points from the sample and being able to use those sample to be able to estimate this specific population parameter. Okay, now the parameter could be an average, it could be a mean, right? It could be a variance, it could be maybe we want to estimate what is the largest object in our population, right? The estimator can be for any number of things. A lot of the ones that we're going to look at today will be means and variations and things like that, but there's actually a pretty big variety of what we could be trying to estimate. Okay, and you'll get a good feel for these, I hope, as we go through the lesson today and as you work through your homework later. Okay. Also, as you start to look at some various IB questions and things like that, you'll be able to see some different ways that we use this and some ways that it can the statistics really are developing in ways that we haven't done before. Okay. One other variable that we're going to use quite often today is a small t, okay? And the small t is an estimate. Okay, so an estimator is some type of function or equation, right, that uses data from the sample. Okay, if I do that and I get a number, that's going to be the small t, which is an estimate. All right, and my hope is that if I get a good estimate, right, that should give me the same value as the actual parameter, the actual value from our population, right? For example, let's say that we're flipping a coin, right? So we've got X is distributed. That would be a Bernoulli, right? We're going to do one time. And, oh, sorry, I didn't mean to do that. That was fun. Comma, probability of 1/2 because it's heads or tails. So we're going to flip the coin a whole bunch of times, right? 100 times, 200 times, doesn't matter. But at specific points, we're going to take a data sample, okay? We're going to pull one out. So this is, you know, this could be on a production line or something, right? When it's developed, when it's creating 200 loaves of bread or something, right? We don't want to have to check every loaf of bread to make sure that it is what we expect it to be, because then every single loaf of bread is going to have a little piece taken out, which I don't think customers would be happy with that. So we take samples, right? So the idea is we do it a whole bunch, right? We're flipping a coin a whole bunch of times, but make the connection to other things that could be done here. And we're going to take 3 samples along the way, or 4 samples, just to be safe. So we'll take 4 samples. I'm going to write that down so I remember and so you remember. So we're going to take 4 samples along the way. So then what we would do is we would say, okay, if we take these 4 samples, right, that means x1, right, would be either a 1 or 0, because either it's a heads or it's not a heads. Let's count heads, okay? So heads is going to be our true value, our success, and a tails is going to be a false. So we can flip it 4 times. That means we're going to have an x1, an x2, an x3, and an x4, right? Because each one of these is a single Bernoulli, right? It's a single thing from this. It's not a normal distribution, obviously. It's a binomial, but each one of these is a single event, right? And so when we put these together, what we would do is we would say, well, the average or expected value of x, or the mean of those, is x1 plus x2 plus x3 plus x4, all divided by how many there are, which is 4. Okay, this right here, this mean that we just took, is an estimator. So we could represent it with a capital T for the average population proportion. It's this, right? Not the proportion. Sorry, it's just actually the mean value. Okay. Yeah. Clean that up. Lovely. Okay. So this, you've done this before, right? This is an estimator. That's all it is. All right. So you could take your samples based off of what these x1, x2, x3, x4 are. You would get a value. Let's say the first one's a heads, the second one's a tails, the next one's a heads, the next one's a heads, right? So we got 4 samples, we got 3 heads, and so then we would go 1 plus 0, because the first one was a heads, the second one's a tails, plus 1, all over 4, and we would get 3/4, which would be our estimate, right? So this would be an estimate for our average number of heads. All right. Now, of course, with only 4 samples, that may or may not be exactly what we want. So that wouldn't be a valid way of being able to demonstrate this. But the idea, I'm trying to illustrate what these variables represent, and it does give you a chance to kind of work with these new parameters and variables with something that you've done before and something that you understand. All right. So I think that's probably good. Let's go on to the next idea, the next scenario. Okay. Good. Here, we're gonna minimize this and keep going. We're gonna keep that, but I do want to talk about a little bit more first. So, yeah, let's keep going here. If I'm using t, so t, if I'm using t to estimate a population parameter, okay, if the average of t, right, or in other words, if the expected value of t is equal to theta, so the average t, or when I take all those little t's together, estimate 1, estimate 2, estimate 3, and divide by however many there are, right? If that expected value gives me the same thing as whatever the parameter is that I'm trying to measure, then we call it unbiased. Okay? If it gives me anything other than that, and we can do this algebraically, and that's what a lot of this unit is going, this section is going to be, is showing whether something is a biased estimator or not. And we'll look at that, and we'll consider that, and does it actually work, okay? But the idea, I guess, that I'm trying to get at is when we do that, we'll be able to know whether it's biased or unbiased. Now, it's possible to have more than one unbiased estimator of a particular parameter. Now, if that's the case, we still want to know, is one better than the others, okay? So when we figure that out, in order to decide is one better than the other, we look at the variance, okay? And if you look at the variance of t, the smaller, the better. Okay, so that's going to be an important idea as we go forward and look at a couple of examples. Okay, so yeah, obviously a smaller variance means that there's less variety in the parameter that we're getting. All right, so actually, I just move on. We'll look at an example right now. We'll look at this example and just try to get an example, an idea of the terminology and what each of these things means and what's going to be expected of us. All right. So here's the first one we're going to do. We're going to look at this one where it says let x be a random variable with unknown mean and unknown variance. Consider samples x1 and x2 of size 2 of independent variables taken from x. Okay, so this fits that scenario that we're talking about. We have a huge population. We don't know what the population is. Okay, that population has an average. It has a variance, which those things we don't know right now. Okay, we have two samples that we're taking out, and they're independent. Obviously, that's going to be an important part of a lot of what we work with is that events are independent. And so now it wants us to show that T1 is an unbiased estimator of mu. Okay, so in order to do that, we talked about this on the previous slide, we're just going to show that the expected value of T1 is the same thing as the mean. All right, so in order to do that, we're just going to take the expected value of x1 plus x2 over 2. Okay, and you know your expectation value. The 2 can be brought out as 1/2, so we're going to have 1/2 times the expected value of x1 plus x2. At that point, because it's expected value, we can write them as separate numbers. So 1/2 e x1 plus e x2, just like that. It'll still be in parentheses. And now at this point, we recognize that the expected value of a single event should be equal to the expected value of the population, right? That's one of the things we mentioned at the very beginning of my previous slide here. And so these both are going to be mu. And so that means I get 1/2 times 2 mu. And so therefore that's the same thing. Sorry, I'm going to save a little bit of space here. Oops, that is not what I want to do. We are going to try to save a little space and say that, of course, then is equal to mu. So we've shown that that is unbiased. Okay. The next question asks us to show that T2 is unbiased. Now T2 is a little bit weird, and you may say, well, why would you use this as an estimator? Well, depends. Are later samples more important than earlier samples, right? Do we expect things as we go on to get better or worse? Students, for example, if this is grades, students may say, yeah, I think this is a better representation of my grade because it's counting the later score more strongly than the previous score. And so an estimator like this would be a way of keeping all the values present, but weighting the later ones more important. Okay, so is it valid? Well, let's see. Let's make sure that it still gives me an estimator for mu. Okay, so if we go through our expectation algebra just like we did before, this one we'll go ahead and we'll split it. Sorry, this should be equals the expected value of that. So we'll split it into two fractions. So expected value of 3x1 over 8 plus 5 over 8, sorry, expected value of 5 over 8 times x2. We can pull out the fractions then. Okay, so expected value of 3 over 8. I got to keep watching my microphone down here. Sorry, that's not what I wanted to do. Once I accidentally turned off my microphone halfway through. Yep. So 3 over 8, expected value of x1, plus 5 over 8 times the expected value of x2. And like we talked about before, expected value of each of those is the mean of the population. So it would be 3 over 8 times the mean plus 5 over 8 times the mean. And what do I get when I add those together? I get the mean. So once again, I do get, when I try the expected value of that estimator, I do get the mean, right? So interesting, I suppose, interesting enough that it gives me the mean, the same thing, both times. All right. So the next question is, letter C, calculate estimates T1 and T2 for the sample 2.1 and 3.5. Okay. So we'll go ahead and do that for each of these. We'll work it right here. So this was the big T. So now we're going to do little t is going to be 2.1 plus 3.5 over 2, which will be about 2.8. And then we'll do the same thing over here. So that was the estimate for 1, and this was the second estimate using the second estimator, which we're going to do 3 times 2.1 and plus 5 times 3.5, and then divide it by 8, and you should get 2.975. Go ahead, make sure you can get that. All right, and so you can see that we get two different values. Even though they're both unbiased, it doesn't mean we're going to get the same results. It just gives us something different. Okay, so the next thing that we're going to do is letter D, which is define the variance. So we're going to do the same thing here that we did in step A and B, except instead of working with expected value, we're going to work with variance. So first we're going to find the variance of the first estimator. We use the same process as before, use that expectation algebra that we learned in section A. Let's just go ahead and write this as 1/2 x1 plus 1/2 x2, right, which is that T1. I've just distributed that 1/2. Recognize that when we pull the 1/2 out, that it's squared. So 1/4 variance of x1 plus 1/4 variance of x2. And then each one of these, right, variance of x1 should be that sigma squared, because the variance of a single event should be the variance of the population. So we got 1/4 sigma squared plus 1/4 sigma squared, and so we get 1/2 of the original variance. Okay, so there we go. We'll do the second one as well. Follow basically the same process there. Variance of the second estimator. Again, it'll be 3/8. The variance of 3/8 x1 plus 5/8 x2. Pull out the fractions, same thing as before, do it separately. So I'm going to have 9/64 variance x1 plus 25/64 variance of x2. And just like before, the variance of x1, variance of x2 are both each going to be sigma, because we expect the variance of an individual event to be the same as the group there. So when we add those together, I should get 34/64 sigma squared, or in other words, 17. That's not a 7. Yep, 17/32 sigma squared, which is just over 1/2. So showing you that this one is not as good of an estimator as the first one. That's actually question E, is which one's a more efficient estimator? Well, this one is, because it has a lower variance, right? The estimates that we get are going to be closer to the actual value, rather than jumping around, which, I mean, you kind of expected that. We know that this is a better equation for the average than this one right here. Okay, but again, it kind of depends on your purpose and what you're trying to get, and that type of thing. All right, I do want to talk about one other thing real quick in talking about biased and unbiased estimators, before we go on to the last example, the last slide, and that is this. You learned in the core that the standard deviation is equal to the summation of all the values from I equals 1 to whatever number, and then you would do xn minus the average, and you'd square it and divide it by n, and then square root it, right? Now, of course, what that means is that the variance is equal to all of that without the square root, right? Now, we were very clear, at least I was very clear back at that time, that this only works when we have the data for the whole population. Okay, that only gives us the variance and or the standard deviation when we have all the data for the whole population. Okay, if we don't, then if you were to do this, remember sigma is the letter or the variable that we use to represent the standard deviation of whole population. We use S for just like we use x bar for the mean and mu for the mean. Mu is for the whole population, x bar is for a sample. Sn would be the standard deviation of a sample. Okay, Sn squared then would be the variance. If you were to use this formula, I equals 1 to n of xn minus x bar squared over n, this would actually end up giving you a biased estimate. Okay, now I'm not going to go through the proof of that. If you want the proof of that, it's on page, I think it's 85 to 86 of your Hayes and Harris option book. Okay, and you can go through and look at that if you'd like. I don't know that the proof is super important to us at this point, but this is actually a biased estimate. Okay, it also on those pages goes through a proof that for it to be unbiased, you have to do this. You have to multiply by n over n minus 1 times Sn should then give us an unbiased estimate. Okay. Sometimes we call that, we write it this way, we go Sn minus 1, 2. So this is an unbiased estimate of sigma squared, which means that the expected value of this is equal to that. Okay, the expected value of this one is not sigma squared. All right, this is why on your calculator it always gives both Sn and this, right? The sigma is the standard deviation as long as you have all the data from the population. This is what we use to represent that it's not the correct. This is once you've made this adjustment, multiplying by n over n. Sorry, it should have been n minus 1. Okay, so what the formula ends up looking like is this: is we say the unbiased estimator for the variance is everything else will be the same. Summation from I equals 1 to n times xn minus average x squared all over n minus 1, because the n is going to be canceled out and we're going to multiply by n minus 1. And this then is the unbiased estimator for the variance. All right, so keep that in mind. That is one thing that does come up quite often. And then from there, go ahead, look at the next question and the next example, and you can wrap it up there. Thanks, guys. Up. All right, so this should be fairly straightforward. We're going to just look at what we've got here, work through the question. It basically random variable, we don't know the mean, we don't know the variance, so fairly typical. It's given us a sample with 1, 2, 3, 4, 5, 6, 7. So it's given us 7 different data points in our sample and asking us to do an unbiased estimate. All right, so the first thing it asks to do is find an unbiased estimate of mu. And we know that an unbiased estimate of mu is just the mean of the sample. Right? We talked about that on the previous, at the very beginning of this lesson. So all you're going to do is add up all those numbers, right? Find the summation. Sorry, that's not a very good sigma. Let's try again. There you go. Add them all up, and then divide by how many there are, which is 7. And go ahead and do that on your own. I don't have my calculator with me. I can't show you on the iPad here, but I worked it out, and you should get 4.07. All right. Letter B asks us to calculate S6 and S7, both as squared. So the variance with the 6 and the variance with 7. All right. So the S6 is that S squared n minus 1. Right? And so all you're going to do is you're going to do the sigma from I equals 1 to 7. You'll add each of the values from x1, x2 all the way up, minus subtract the average, which we just calculated right there. So you should be able to just put that in. And then you'll square it, of course, and divide by n minus 1. Sorry, that should be a 1. Man, my brain is off. N minus 1. And so once you have that, then that n minus 1, n is 7, so this would be 6. And you should just be able to work through that and calculate it, and you should get close to 7.21. All right, go ahead and make sure that you're comfortable with the sigma, doing all that, and that you do end up with 7.21. All right, the second part, II, it asks us to do exactly the same thing, but this time don't do n minus 1, do the n. And so again, you'll do the sigma, I equals 1 to 7. If you've got your calculator on, you probably don't need to do all this over again because you can see what you got when you did that. And this time, instead of dividing by 6, because it's a 7 down there, we're going to divide by 7. right? So this one should give you 6.19. Now, our discussion from the previous slide says, well, this one is biased, and this one is unbiased. Okay, so now this asks us to write down the expected value of S6 squared and estimate of S7 squared in terms of sigma squared. Well, because this one is unbiased, then that means the expected value of that variance should just be sigma squared, right? Because if it's unbiased, the expected value of that should be equal to the population parameter, which is the sigma squared. Even though it's unknown, we know it's unbiased, and therefore it should give us that. This one, because it's slightly different, this is just the expected value of S7 squared, that variance. If you think back to the previous slide and the relationship there, you should recognize that this one will be n minus 1 over n, which would be 6 over 7 times sigma squared. Now, the reason why you're getting a smaller number is because, remember, this is a random variable. Let's consider, for example, a normal distribution. It doesn't have to be a normal. It can be any type of distribution. But if I were to take 5 samples from this, right, I might get 1, 2, 3. I'm just randomly marking spots, marking 5 different spots there. Those are the data points that I'm going to get. So if I were to calculate the variance of those 5 points, then I would get a variance for this. And you recognize that the variance you'd get here would be smaller than the variance of the whole distribution. And so that's one problem. Yes, it is a smaller variance, but it's not really the variance that we should be getting if we were to consider all the data points that it's unlikely for us to get if we are taking random samples, right? So the last question is, of course, which of the estimates is the preferred one? And the answer is, well, we want the unbiased one, right? Even though the variance here is lower, that is a secondary issue to the first one. And so first, we got to make sure that it's unbiased. Secondly, we look at which one has the smaller variance, okay? And that's it for this part. Let's go on to let's move on and finish this up. All right, so I do want to wrap this up with just this last slide of what makes a good estimator. Okay, well, of course, the first thing we always look at is it unbiased? Okay, we want to make sure that our estimator is unbiased, that when I take an estimate, that it actually gives me the value that I expect, right? So if the remember, this is our population parameter. Okay, so if this is the mean, then when I go through and calculate this estimate, then the expected value of that estimate should give me the mean, right? If I'm looking for variance, the expected value of that calculation should give me the variance. Now, we understand that when this actually goes into practice, that the actual estimate might not be perfect, right? Because the estimate itself, a specific estimate, depends on the samples that you take. Remember the very first slide I was talking about flipping a coin 4 times, and I ended up with 3 of the 4s being heads, which is possible, right? That's not unlikely. It's not improbable. That could very likely happen. So if I did have 3 out of 4 heads, then the estimate that I got would be 3 out of 4, even though I know that the average number of heads should be 1/2. But the hope is, if I do this over and over again, right, T2, T3, T4, T5, right, if I do that, then the total average of those estimates should give me the estimator, right? The expected value of the estimates, or the average, when I put those together, should give me the estimator, which then in turn should give me this population parameter, whatever it may be. So we will be looking at that sooner or later. What is the distribution of these population parameters, of these estimates? Okay. Now this kind of should start clicking in your mind saying, oh, wait, we just did the central limit theorem where when I take a number of samples, they should be around this mean. and the more that I mean, you should start being able to make some connections with some of that stuff that we did last lesson, okay, or the last two, I guess. The next thing is we want the variance to be low, right? Now, of course, this comes first. Having it be unbiased is number one. But if they are unbiased, then the next thing we look at is variance. And there's a couple of different ways you can do that. You can actually calculate the variance sometimes and find out which of the two variances is lower. We did an example where we had one where it was a half of the variance versus what was it, 5/8 of the variance. And we, or actually it wasn't even that, it was a different number, but you get the idea. You might be able to do something like that where you calculate and figure out which one relatively has a lower variance. In another situation, maybe they give you an equation for variance, right? I don't know what the situation would be, but what if they said the variance of x is equal to, and this is your estimator, right? This is t, your estimator for the variance of x. What if they said it's like a, and then take your first sample and square it, and then take the second sample and multiply it by a squared, and then divide by 2 or something. This obviously isn't the case, but you could be given some type of formula that represented the variance, right? Or represented that estimator. Now, what if they wanted you to minimize that? Well, that's just optimization, right? How do we optimize this? Well, we take the derivative with respect to the variable that we want to optimize, and then you should be able to take the derivative and then solve for the a that gives the lowest, or the 0, right? We actually want this to be 0 in order to have the minimum, and so you can do a normal optimization question, right? So I want you to just kind of be open, aware to how this topic could be integrated with some of the other things that we've done. All right, and that's it. That's it for today's lesson. I'd like for you to go ahead and spend some time now working on that exercise F in Hayes and Harris, and just kind of see how far you can get on that. All right.